My name is Vivian Kim, and I'm currently serving as the Operator Certification Coordinator here at ADEQ. Please hold all of your questions until the end of each presentation. We will answer them before we go on break. To start off, I'm going to pass it off to Danielle, who will be presenting today on groundwater sampling and calculating the Geomean. Danielle, feel free to take it away.
Hello, my name is Danielle Duncan. I'm with the DEQ Groundwater Inspections and Compliance Unit, and I'm the Compliance Case Manager. And I'm going to discuss groundwater sampling and calculating the Geomean today. And so first we're going to start out with groundwater sampling for the first half, and then the second part we'll discuss calculating the Geomean. So groundwater sampling. Why do we sample groundwater? It could be for permit requirements, monitoring, the APP, the Aquifer Protection Program. We require groundwater monitoring on down gradient from wastewater facilities, mining facilities. And then you may also have to do groundwater sampling for ZIPDs, for the Arizona Pollutant Discharge Elimination System, for those permit requirements. Other times we just want to evaluate quantity and or quality of groundwater. What is the quality of the groundwater, and do some analyses on that. How do we sample or access groundwater? We've got generally, you'll have a groundwater well, and a monitoring well generally will be dug down to the groundwater table, usually down gradient from your facility, or if it was a private home, wherever it would be there. And it'll be screened at a certain interval where we want to capture the groundwater table in the area. And there's many methods for sampling groundwater, but in general, we usually use either a baler or a low flow sampling using a pump and tubing. We can also use passive samplers. A baler is essentially, think of bailing water, from a boat out of a bucket. And so a baler is really just a little cup that we send down the well, and it fills with water, and we pull that up, and we essentially bail out the groundwater. Really, the industry standard is low flow, and you're using a pump and tubing. And so in that case, we're just sending tubing down the well, turning on the pump, and then capturing that groundwater to sample that way. There are passive samplers that you would leave in the well. I don't usually see that with our wastewater facilities and so forth. So the advantages of using a baler, kind of like a little bucket, just very simple. This is just a cup that we dip down in the well, and go ahead and grab the groundwater that way. The advantages is that there's no power source. It's portable, also inexpensive. You can use the same baler for the same well, and you don't have to worry about cross-contamination. Them being inexpensive, you can also, just use a new one every time. And really you're reducing the chances of cross-contamination because you've only got a single baler cup to access that groundwater. As far as volatile organic compound sampling, you're having minimal outgassing because you're just kind of just filling up this cup, and you're not stirring up the water. You're not outgassing any volatile organic compounds. And the baler, just kind of by the way it works, we're accessing the most stagnant water first. So whatever there is on top, that's what you're pulling out first with a baler. And so it's also useful if you just have small amounts of purge water. and you just want to, literally bail it out. Again, think of, a boat and a bucket, and we're just using a bucket to access the groundwater and pull our samples. But again, it's really not the industry standard, and I think in contaminated sites, cleanup and so forth, we don't use balers, and to my knowledge. Low flow is really what we usually use. And when I say low flow, it's because we're using tubing, and instead of getting, maybe a half a liter, a quarter liter of water with a baler, we're getting smaller amounts of water using tubing, which is usually maybe a quarter inch. And so we've got to have a pump to pump that water through the tubing and into our sample cup. And so it's the peristaltic. There's two types usually of pumps that we'll use: a peristaltic pump or a submersible pump. The peristaltic pump is portable, but we can't reuse that tubing. And in any case, we can't reuse the tubing unless it's dedicated tubing to that well. We don't want to cross-contaminate from one groundwater well to another groundwater well. And the advantage of using a peristaltic pump is that it's portable. We could take it from one facility to the next facility. But again, we need to have fresh new tubing for each sample that we take from each different well, because we don't want to cross-contaminate that. Many folks use a submersible pump, and that is dedicated down in the well. The pump stays in the well, and you've got your tubing, and you just access the well, and it's already down there. And the advantage of that is that we don't need new tubing. It lives in the well. It stays with that well. It's dedicated, and we're not going to worry about cross-contamination because we're only using it for one well. And so kind of why I wanted to discuss this today is that when we're sampling groundwater, it's very important that we purge and stabilize the well. And I'll have a slide showing the language in the Aquifer Protection Permit, which talks about that. But it's very important that we purge and stabilize the well. And that's because we want to make sure we get a representative sample. And that's true for any media that we sample, whether it's soil or air or water, groundwater. We want a representative sample of the groundwater formation. And so we don't want, the stagnant water that's sitting in the casing. So when you've got a groundwater well, you've got water sitting there, and presumably the groundwater formation is flowing through the screen of the groundwater well, but that water may be, somewhat stagnated in the well. And so I found my experience with the APP program that some facilities, if they're not purging the well properly, we can have some issues, and I'll talk about that some more. But again, getting a representative sample. And so the first thing is purging the well. We want to purge the well 3 well volumes. And there's a calculation, I didn't put it on here, but there's a calculation that you can do based on well volume to calculate how much volume is in the well. And again, we want three well volumes purged before we sample the well, because we want that groundwater formation. We want the groundwater that's in there. We don't want that water that's sitting in the well, kind of maybe getting funky. And so purging the well is very, very, very important. And we should be waiting until parameters are stabilized. And I'll show you the different parameters, but we want to make sure that we're getting into that groundwater table and that it's representative. And again, purging the well. at least 3 well volumes. And the calculation is useful, but again, you kind of might have an idea of how much water is in the well. But again, as long as you're purging it to what you believe is 3 well volumes and just purging that old water out. And so we're removing that stagnant water. That could be using a baler or using the pump and tubing. And this is where the pump is really useful, because we can measure how much volume we're removing from the well. And so when we're purging that water, we're pulling the water out of the well. And so we're causing groundwater to be replaced from the formation into the well as we're pulling it out. We're pulling the water out, and so we're accessing the groundwater formation. And so a kind of a note, and especially in Arizona and different places, sometimes we could purge that well dry. And then they could be slow to recharge. And I understand that, sometimes maybe operators don't want to spend the time to purge the well, or they purge it dry, and that's okay. But then, based on your experience with that well, you'd have an idea of how long it takes that well to recharge. And once it recharges, then you can sample it. And again, we want to access the groundwater flowing, through the, past the facility, under the facility, not the water that's just kind of sitting in that casing. And if you do purge it dry, again, that's okay. But once it refills, we want to go ahead and sample that. And so our stabilization parameters, when we use a low flow sampling pump with tubing, oftentimes, and it is in the permit language, and I'm not sure that we're always doing it, is that there should be a flow through cell that measures pH, specific electrical conductance, called EC or SEC, oxidation reduction potential, or RP, turbidity, and dissolved oxygen. The pH, I think everyone's familiar with that. We want to go ahead and while you're using the pump and you're pumping water through the tubing and through your flow through cell that's making these measurements, we want to wait until the pH reading that it provides is plus or minus 0.1, so maybe 6.9 and then 6.8 and 6.9. And I'll show you a little bench sheet on that. Your specific electrical conductance, this is a measure of the salts in the water and the conductivity of the water. And on this, we're looking for plus or minus 3%, and we're measuring stability of the groundwater before we sample it, making sure that we've adequately purged it and that we're getting at that groundwater formation. And so also with oxidation reduction potential, it's going to give you a reading. You're going to want plus or minus 10 millivolts. Turbidity, I think we're all probably familiar with turbidity. That's the measure of kind of how clear the water is, how well we can see through it, how many solids are sort of floating in there. And this is important with purging. When you first start purging, you may have a lot of turbidity. There may be, some sedimentation in the well. There may be you're stirring up that sedimentation. And so we want to make sure we're at plus or minus 10%, especially if it's turbid. Ideally, though, the well is screened, properly, but you will get sedimentation over time. And so we want to make sure that our turbidity parameter is stable before we move on. Same with dissolved oxygen. That kind of speaks for itself. that's the amount of oxygen that is dissolved in the water. And on that, we want plus or minus 0.3 milligrams per liter. And so here's a picture of what I've sort of been talking about here. And there's different brands. Aquatrol is pretty popular. So here on the far right, going to the left, we have our tubing, and we put that's down in the well, and there is in this case, there's not a dedicated pump in the well, it's outside, but you start the pump and you're pulling water through, and then it comes through this flow cell, which is making all the different readings. And nowadays they're super slick. It can be hooked up to your phone, and you can right away look at your stabilizing parameters, and you keep pumping until those parameters are stabilized. You're not getting bouncy pH or bouncy turbidity, so forth. And so to the left of that Aquatrol is your bucket with your purge water. And so you're pumping and pumping and purging until all your parameters are stabilized. And then finally, to the left of that are your sample containers. And this is an example of a bench sheet, if you will, or a field data sheet where we put the time, we put the groundwater well we're sampling, and they've taken these measurements of pH, specific conductance, temperature, dissolved oxygen, ORP, turbidity, and the water level. That's another data point that I've noticed isn't always collected. And knowing what your water level is actually really important, and it's a good idea to monitor that over time. Over time, the depth to groundwater, the depth from the ground to access the groundwater table, that can increase over time as groundwater is maybe pumped in the area for agriculture or for drinking water or just naturally. And so I really encourage everyone to record the depth to groundwater. And sometimes we can correlate the depth to groundwater over time with contaminants such as maybe arsenic or selenium or nitrate as the groundwater recedes deeper in the ground, or alternatively, we can have seasonal changes in groundwater, in the depth to groundwater. Say we have a very rainy summer, then it may be shallower. The depth to groundwater may be less than it is in the summer. And so keeping track of that is pretty useful. And sometimes when the depth to groundwater gets shallower and the groundwater meets with shallower soils that may be affected historically with nitrate due to past agricultural practices, or maybe there's an arsenic or a selenium natural formation that isn't a problem except when the groundwater table is high. And so I really encourage people to do that. And a good point to also make, and I know in the aquifer protection permits, if the groundwater well is dry, we have a Smurf code for that, but the permit requires that we drill a deeper well. We can't just discontinue sampling the groundwater. Another important thing to keep track of is how much purge volume you've removed. So we see at first they've got a 1/4 gallon, and then 2 gallons, and then 3.5 and 4. this is a good thing to keep track of and keep this data at your facility. So in case, you know, maybe someone new comes, they have an idea of how much purging they need to do, how many gallons need to come out. And we can see on this data sheet, you know, the temperature is stable right around 20.5, 20.8, kind of looking for plus or minus 10% or 20. These flow cells tend to, it can be kind of bouncy. You've got to kind of wait till you've got a kind of consistent reading. But if you're provided with, you know, a history of keeping these bench sheets, then we can look at trends over time as far as the depth to groundwater and then how much water we can expect to purge before it's appropriate to sample the well. And so here is actually APP permit language for your wastewater facility or maybe your mine site. And so, and it's laid out in the permit, and we encourage everyone, read your permit, whether that's a ZIPTES or any type of permit. It's really important just to read the permit, be familiar with it. And the permits for the APP program specifically mention that, you know, static water levels, this is the depth to groundwater, this shall be measured and recorded prior to sampling. And wells shall be purged of at least 3 borehole volumes. And again, there's a calculation for that, but it specifically says that we need to measure the depth to groundwater, and we need to purge that well at least 3 volumes, or until field parameters, the pH, temperature, conductivity, are stable prior to sampling, whichever represents the greater volume. So, you know, 3 well volumes and or your stabilizing parameters. But I do encourage, just do the 3 well volumes purging, and chances are your parameters are going to be stabilized after that. And the permits do say if evacuation results in the well going dry, then you should allow it to recover to 80% of the original borehole volume, or for 24 hours. Sometimes people don't realize this, that we can purge the well dry and then come back the next day. So, you know, we don't need to sit there for 8 hours or something. We can come back the next day and go ahead and sample that well. Now, if after 24 hours there's not sufficient water for sampling, then we record that well as dry for the monitoring event. And we have a SMRF code for that, and I believe ZIPTES as well. And then it says an explanation for reduced pumping volumes, a record of the volume pumped, and modified sampling procedures shall be reported and submitted with the SMRF. And we noticed this in the APP program, that sometimes people report the well dry a couple of years. And then we go, oh, you know, goodness, you know, we need to get a new well, or maybe we get with the permitting team and see, is it appropriate to drill a new well, or maybe we don't need to do any more groundwater sampling. But a dry well does not mean that you're done groundwater sampling. And then some boilerplate language. The permittee may conduct a sampling using low flow purging methods, which we discussed with the pump and tubing. And we always want to be in accordance with EPA, USGS, or DOD protocols. The well must be purged until indicator parameters stabilize. And indicator parameters shall include dissolved oxygen, turbidity, pH, temperature, and conductivity. And so this language is written into the permit, and so an inspector may ask for this data. And So you want to make sure that you have that bench sheet and you have that data. And if you've got, you know, maybe some violations of nitrate or, you know, maybe background arsenic, we first want to make sure that we're sampling correctly, because sometimes and oftentimes, you know, sometimes violations really are a sampling error. And so it helps us at DEQ to understand the problem if everyone collects the proper data that is required in the permit. The more data we have, the better, because we can better understand you know, why the groundwater is the way it is, or if we have any violations. Oh, nope, doesn't want to. There we are. So I know the APP permits, and I believe the ZIPDs permits require you to sample for, you know, coliform and nitrate, nitrite, TKN, so forth, and metals, usually maybe quarterly or semi-annually. And then also the permits require facilities and folks to sample for volatile organic compounds. And when we're sampling for all the other things like metals and coliform and so forth, those are sort of more stable parameters, more stable potential contaminants. Volatile organic compounds, on the other hand, by definition, are volatile. That's the key word. And we're talking about chemicals like benzene. We're talking about, you know, things that outgas, all your hydrocarbons, benzene, naphthalene. Think of when you're pumping gas and you could smell the benzene and all of the hydrocarbons. And so the fact that we can smell those, they're volatile. They're outgassing into the environment. And so when we sample for VOCs, we want to there's a special procedure, because we want to make sure that when we're sampling the groundwater, we're not losing those VOCs if they're present in the groundwater. And so we always want to collect your VOC samples first. And we want to minimize, you know, disrupting or stirring and off-gassing of VOCs. You know, if I have a sample container for VOCs of water and I shake it up and I stir it up in open air, and if there's VOCs there, then I might smell that coming off. And so we want to be really careful when we're sampling and when we're transferring the groundwater from, you know, the pump and tubing into your vial. And something very important, and you'll see it on, you know, the Test America and all the different urethans now. You'll see them, they want a convex meniscus in the vial. And so convex means that, like a bowl, the curve is at the bottom. And we want no air trapped in that vial. And that's because any of those VOCs, naphthalene, so forth, we want them to stay dissolved in the groundwater. We don't want them in the air of the vial. We don't want to provide them extra air in the vial. And so we would take our tubing and just minimize the amount of disruption and get that water into the vial without disrupting it, and then no air. And the procedure is you get your groundwater in that vial, get it all the way full to a convex meniscus, close the cap, and then wait at least 10 seconds to make sure that there's no air developing at the top. And again, the idea is that we want to trap the VOCs in the water, and we want to keep them in the water all the way until the lab, right? So don't stir it, don't shake it. Now, if there does develop air in there in your vial and you don't have a convex meniscus, then you need to go ahead and resample. It's very important. And when it gets to the lab, they're going to look at those vials and make sure that there's no air. And similarly with coliform samples, you'll find that Eurofins Test America, there's a little line where they want that sample volume filled to, and they can be very particular, and it needs to be right on that line. And you don't want to collect all your samples, get down to the lab, and have them say, these aren't going to work, or you get a flag. They'll flag those samples saying, they weren't proper, they weren't received properly. There's air in your VOC vial, or there's not enough sample in your coliform, and so forth. And so again, VOCs, kind of a special procedure because they off-gas, whereas your metals and your coliform and so forth, they're not volatile. So sample your VOCs first and be very careful when you're doing that. And then make sure, watch it for 10 seconds and make sure that you've got no extra air. And so common issues that we run into, again, inadequate purging. I can't stress this enough. I've talked to facilities and say, did you purge the well? And they go, what is that? Well, that's super, super important. All that sediment and kind of, funk sitting in that well, that is not representative of the groundwater formation. Another common issue is contaminated sampling equipment. And this can be especially true for wastewater facilities, kind of by definition. Coliforms are a natural bacteria, and if we are doing our job at the wastewater plant, it's very easy to have, maybe fecal coliform, maybe regular coliform on our hands. And so it's very important to use clean gloves, to use clean sampling equipment. Even the cooler that you use to transport those samples needs to be clean. Not only with coliform and fecal coliform bacterial analyses, but the same for VOCs. I've seen in the past where people sample groundwater or even soil, but then they're in a work truck. Maybe there's oil, or maybe they pump gas or spill gas. You can contaminate your samples with gas, or even near the exhaust pipe, or maybe someone smoking a cigarette. So we want to make sure we have clean sampling gloves, clean cooler. Even we don't use blue ice here, but your ice bags. You just want to make sure that we're not introducing contaminants to our samples. And that goes for groundwater, soil, surface water. Anytime we're sampling, we surely don't want to spend this time and money and have it come up. And I've had that come up where it's contaminated with coliform. And specific to the groundwater wells, the casing should be sealed, and then the top casing should be sealed. There should be no water infiltration to the top of the groundwater wellhead. Coliform is kind of ubiquitous in the environment. If we have soil or, any sort of things that are introduced into the top of the well, and so I know when I do my inspections, I'm making sure that the top of the well is totally sealed. there's usually an additional cover to the well because we don't want, you know, wildlife or something getting in there with coliform. And while we're on that subject, if you know that all your sampling equipment and your gloves are clean and you're still having coliform hits in your groundwater, then, you know, we need to look at whether our well is not properly sealed or maybe it's cracked. And so again, the top of the well casing, and then people will send you know, cameras down the well to make sure that it's not cracked. If it's cracked, you know, near the top of the well, then we're introducing shallow soils, we're introducing bacteria, and so we always want to make sure, you know, when we're sampling and we're getting violations for coliform or something like that, first check our sampling protocol and then check our well to make sure that it's not damaged. And another parameter that sometimes you know, can be flagged at the lab is that your hold temperature is not met. This is especially true for coliform bacterial samples and also VOCs. So you want to make sure you have a good cooler, you've got your ice, you get it down to the lab. And I understand that some of our more remote communities, this can be a challenge. You know, maybe the lab's not, you can't get it to the lab on Friday. That's fine, we understand that. And then that's where the holding time comes into play. And again, this is very important for coliform and VOCs, but mainly for your bacterial analysis. You know, we have that sample, we want to count the number of bacteria that are in there at that time. If we let that sample container set for, you know, too long, it's a 24-hour, I believe, hold time, then, you know, those bacteria are multiplying or perhaps they're dying. And so it's really important. And I should have put on this slide, but the coliform container, Testamerica urofins, I mentioned they put that fill line, and that's on purpose. We don't want to give them too much air, but if we fill that container all the way with water, then the coliform in that don't have any oxygen. There's no air in the container to go into the water, and then all of our bacteria have died. And I think everyone knows when you get to the lab, you know, you've got that person up front and they're checking the temperature, they're checking your sample containers to make sure that they're appropriately filled, they're at the right holding temperature, and they've arrived on time. And if those things are not met, then your samples could be flagged, and then that data, you know, may be questionable. Some other issues, and I touched on it, your coliform detections, I kind of can't stress it enough. The well casing at the top must be sealed. We want no surface water, no rain, no birds, no bugs, nothing getting in there. And again, your gloves, your sampling containers, everything needs to be really clean. Wash your hands, put on fresh gloves, especially for the wastewater facilities. By definition, you know, we're kind of working in a bacteria-rich environment, right? So we want to take that into account. And again, we've had, you know, nitrate detections, selenium detections, arsenic detections, and oftentimes that's because that water is just sitting in the well, and we're not accessing the groundwater table as it's flowing today. We don't want that old stale water. We want the groundwater formation as it is today. Now we'll move on to calculating the geomean. This is, I believe, but I could be wrong, specific to aquifer protection permits. And usually this will be a total nitrogen calculation, and I'll show you the permit language. So what is the geomean? Why would we calculate the geomean? And again, it's an aquifer protection permit requirement. Not all permits require it, but some do. And then just a couple of verbal explanations is that we're multiplying the amount of numbers that we have together, and then we're taking the nth root. And then another way to say it's an average that multiplies all the values and finds a root of the number. And I'm going to show you that. Well, first, here's the permit language. So your regular discharge monitoring, if you notice on the bottom, this is very common with APP permits, total nitrogen, 5 sample rolling geometric mean. And I actually really like this parameter because it's a 5-month data point. So as a regulator, I can look at your 5-month rolling geomean nitrogen values, and I can tell a longer time frame of compliance or non-compliance by looking at that geomean instead of a snapshot in time. And the permits often do also have, total nitrogen, daily value, nitrite, TKN. But this rolling geometric mean, for me as a regulator, is an indicator of the long-term state of the plant. What's your nitrogen at long-term? And the limit's usually 10. And so here we have the calculation. And so the difference, so a usual average, right? We add the numbers up and we divide by the amount of numbers. So a 5-month rolling geomean, we're going to take 5 months worth of data points. Here I've got January through May. And so a regular average, we would add those numbers up, divide them by 5. That's the average. A geomean, on the other hand, we take those same 5 numbers, we multiply them together, and then we take the 5th root. We're going to take the root of however numbers we have. So instead of dividing by 5, we're taking the 5th root. And there's no way in the world probably anyone's going to calculate this by hand. And so luckily Excel has a great function. It's called equals geomean, and we calculate all those numbers using Excel, thank goodness, right? And you'll notice here, the average of these numbers is 23.8, but the geomean of these numbers is 19. And so I believe the geomean is a more accurate statistic of the central tendency of the numbers. And so I found sometimes operators aren't calculating this correctly, or they're giving us the average. And you can see it makes a difference. It can make a difference for sure. And again, for me, it shows the long-term compliance of the plant over a 5-month period. And that's the end of my presentation. And I'll take any questions anyone has.
Hi, Danielle. Thanks for your presentation. We did have a few questions for you.
All
the
right.
first one being is, where is the water going after the bucket? Can you give more information on the flow through cells? Some places have very deep wells, like town of Clarkdale. Monitoring wells and takes a lot of water get moved.
Yeah, great question. And I should have mentioned that purge water at a wastewater facility, you want to hold on to that water until you have results. And the issue is that we want to make sure that that water isn't contaminated, right, with maybe hydrocarbons or so forth. And so we collect that water. And if we were in like a hazardous waste site and so forth, that water would be treated as hazardous waste. But in general, a wastewater facility, that purge water could likely just be reintroduced into the beginning of the plant, because chances are it's not hazardous, and I would just put it back into, maybe your influent or so forth. Oh, and as far as the depth of purging a lot of water, as long as you purge 3 well volumes, and asking about the stabilization parameters, these AquaTrolls are really great. You can get them sometimes for $1,000. And it's just really great. And it can show the regulator that, we purged the well and that the parameters are stable. And it just really kind of gives you peace of mind that we're getting an accurate representative sample.
All right, thank you. We have one more question. Oh, sorry, two more. A question on data sheet. I am confused about the stabilization of data. The data points did not stabilize. All of the data except DO kept changing.
Sure. And yeah, it can be really tricky. If you've got, 4 out of 5 of your parameters are stable, specifically pH, temperature, and conductivity, then I would say you're good to go. As long as, 4 out of 5 or, the majority of parameters, you're going to have some things that are going to be bouncy and some probes, over time, maybe they can be bouncy. But as long as, the majority of your parameters and you feel comfortable, I would say you're good to go.
Okay, one last question is, how do you describe a low flow method as opposed to a normal flow method?
Sure. I would say all of the industry standard is a low flow using these little tubings and pumps. I would say there's few cases in Arizona where we've got so much groundwater that we can pump out gallons at a time. So we're usually using low flow, and you can use a baler, but again, it's usually low flow. All of your groundwater sampling pumps use, I think, 1/4-inch diameter tubing, and it's always going to be low flow. And again, we don't want to, take out all the water in the formation and leave it dry. We want to purge it until the parameters are stabilized, but we want to make sure we leave some water in the well to sample, or if it goes dry, we'll come back the next day.
All right, well, thank you so much, Danielle, for your presentation.
Thank you.